In this video, we're going to talk about transfer functions, an important concept in process control, and how we can use Laplace transforms to find these. Transfer functions exist in the Laplace domain, and that's why it's so important that we utilize this tool to solve the time-dependent ODEs we encounter in dynamic systems and process control. Let's talk a little bit about transfer functions. So when we apply Laplace transforms to a dynamic process model we develop from first principles, we can really understand how to design control systems to control that process. Remember that we've got to use first principles like mass balances, energy balances, thermodynamics, all the different forms of transport equations we learn, and also chemical equilibrium and reaction kinetics to create these models. Once we have a dynamic model, we're able to formulate a differential equation that we could solve using Laplace transforms. So we want to first of all take that differential equation and transform it into an algebraic equation in the Laplace transform variable S. So we've eliminated the dependence on time and have equations that are algebraic equations of S. Next, we can solve that transform of the output, so that's the dependent variable. That's as we did in the previous examples where we made an explicit function of the dependent variable. And finally, to find the time dependence of this dynamic system, we could invert that transform to obtain the solution of this ODE, which is obviously the response of the output variable as a function of time. So just to sum it up, we can think of the Laplace transform of the controlled variable is equal to the transfer function, so some function we could determine by algebraic manipulation multiplied by the Laplace transform of the input signal. Okay, so that's very interesting. So if we think about the controlled variable Laplace transform as y of s, so the Laplace transform of the dependent variable, or dependent variable, that's right, and the Laplace transform of the input independent variable as x of s, we could see that the transfer function can be defined as the ratio of these two, dependent to independent variable. All right, in that way, it's very interesting to look at the properties of any process's transfer function. It tells you a lot about the dynamic behavior. So let's look at it and just draw a little sketch. So as we just said, the transfer function can be defined as the ratio of output to input for any process. So let's draw a little block diagram. We often use block diagrams to represent what's going on in a process control scheme. So here we have the input to the process. This is represented in the Laplace domain as x of s, and the output of the process, okay? And this is represented as the dependent variable y of s. And the process itself is represented by this block. Inside the block, we'll put the transfer function. It's very convenient that different processes take on familiar forms. For example, we'll encounter many first-order processes. They take on the transfer function of the form k over tau s plus 1, where k is the gain. So after a very long time, when there's a steady state achieved after some change in the input, k is the absolute ratio of output to input in the frequency domain. And here, tau is the time constant, which is a measure of the dynamics of this system. How fast does it change with some change in the input? Right, so we can look at that in the block diagram. Right, these transfer functions are very useful, and they take on different forms as well. If a process is second order, for instance, it'll take on a unique transfer function, and we'll see that later on in later lectures. So normally we assume or define conveniently that our initial conditions are at steady state and all time derivatives are zero. That means that when we start a problem, we assume that everything was constant and suddenly at time equals zero, something happened to upset our process. Now our process control system has to intervene to maintain that controlled variable at its set point. Okay, so let's look at an example of a transfer function determination from an ODE. So just in your mind, you can think about how you can derive ODEs from first principles based on the specifications of your process. For instance, in this case, we have a second order linear non-homogeneous ODE, and we have some initial value constraints. This time, both y and its first derivative with respect to time at time equals zero are all zero. So we'll approach this in a similar fashion, but keep in mind the goal here is different. Instead of being asked to find the unknown function y of t, we're looking for the transfer function. Sometimes that's enough to do full analysis of these process dynamics, especially for programming systems. So remember, this means we're looking for y, the output, the dependent variable in the Laplace domain, over x of s, the independent variable, the input in the Laplace domain. So this will be our transfer function. This is what we're asked for. Okay, so let's go ahead with our goal in mind. Let's work on this problem. So just as we did with the ODE initial value problems, we're going to take the Laplace transform of this function and apply the linearity principle once again and distribute the Laplace operator across these terms. So now in the first step, I'll end up with 9 times the Laplace transform of the second derivative of y with respect to t plus 6 times the Laplace transform of the first derivative of y with respect to t plus the Laplace transform of y, and this is all equal to the Laplace transform of 2x, which is a function of t. We're sorry, running out of room there. Okay, so in this case, we can go term by term and write down what the result is from this transform. So according to the second derivative, and if you need to go review your principles of derivatives, we could define that first term as, first of all, 9, and I'll start with some brackets, times s squared times the transform variable y of s minus s times the initial value condition for y, which is 0, minus the initial value condition for y prime, which is also 0. Okay, for the next term we have 6 times the Laplace transform of that first derivative, which is s times ys minus the initial value condition 0, plus y of s, the Laplace transform of y, is equal to 2, we'll factor that out, times the Laplace transform of this variable x. Now it's important to know that in this case, we don't know a whole lot about that variable x. It may or may not be a function and it could change. We could actually develop this transfer function, and even if the function type or magnitude changed for x, it would still be valid. So let's see if we can manipulate this function. So first of all, I'm just going to rewrite this function a little bit. So 9s squared y plus 6sy plus y equals 2x. All right, remember our goal is to get y over x, the transfer function. So all I have to do is factor out y on the left side and divide both sides by x, and I see that the transfer function here is 2 over 9s squared plus 6s plus 1. Very interesting. So that's actually representative of a second order transfer function. A second order transfer function takes on a familiar form. It looks like this: k over, this is like a different tau, squared, s squared plus 2 tau zeta, that's a zeta, sorry, I don't know what, plus s plus 1. All right, and we could see there. So very interesting stuff. We'll talk a lot more about transfer functions and what they mean and how we can use them in a process control system in the coming weeks.